monoclinic crystal system, we have all the bond lengths or edges unequal and two bond angles will be equal to 90 and one beta angle will be not equal to 90. Possible packings are primitive and end-centered. These are end-centered packing. And examples are monoclinic sulfur and sodium sulfate. Next crystal system is hexagonal. Hexagonal crystal system have two edges equal and one is unequal to first two bond angles will be 90, one angle will be 120. Only one sort of packaging is possible in hexagonal structure, that is primitive. Graphite, zinc oxide, cadmium sulfide, these are the examples of hexagonal packaging. We are having a rhombohedral or trigonal. In this, again, all edges are of equal length, but all angles are equal but not equal to 90. It also having a primitive packaging, calcite, which is calcium carbonate, mercuric sulfide, known as cinema, are examples of rhombohedral crystal system. Triclinic. In the triclinic, this is most asymmetric crystal system possible, in which no bond angle or no bond length is equal, and they are not also equal to 90 degree. And only possible packaging is primitive here. Potassium dichromate, copper sulfate, boric acid, H3BO3, they are examples of triclinic crystal system. Now let's have a look at closed packed structures. If we arrange the atoms in a single dimension, that is a single line, only a single straight line is possible. Now let's try to pack them in a two-dimensional space. In a two-dimensional array, two different possibilities are here. First is the second row is placed such a way spheres of two rows are aligned horizontally as well as vertically. Horizontally as well as vertically they are aligned in the same line. They look similar. And this is called a square closed packing. You see here each void surrounded by square. Now another possible packing is when we place all atoms such that second row is placed in the voids or depressions of first row. That's what we keep on repeating. In such case, each atom is surrounded by 6 atoms, you can see here. So this is called a hexagonal closed packing. Now let's pack these two-dimensional sheets into a 3D structure. in a 3D space. If two-dimensional hexagonal closed packing layer placed over similar layers such a way that the sphere of the second layer are placed in the depression of the first layer, like we are getting two different sort of voids there. So what we saw there, we take a first layer, when we place the second layer of the hexagonal closed packed system, then it happens in such a way that they are placed over the void. For example, let's say this is the first layer and this is second layer atom. It always sits over the void or depression of the first layer. When it happens, we are getting tetrahedral arrangement around a void known as this. So this is called a tetrahedral void. Another possibility is known as a octahedral voids. What it is? It happens when void of one layer is placed over the another layer void. In such a case, we are having a 6 atoms surrounding that void known as octahedral void. Now, without further going to the complexity of it or calculations, we just remember the simple point. If in such a hexagonal packing we use n atoms, then we will have n octahedral voids and 2n tetrahedral voids in that system. That's what we saw. This is how the packing will look like. If we look at it, this is the one layer. You see, second, this is the one layer and this is the second layer below it. Here, this layer covers these bottom layer voids, these atoms, right? And here, these layer voids cover bottom layer voids. These are octahedral voids. 1, 2, 3, 4, 5, 6 and 1, 2, 3, 4, 5, 6. But you see, for every octahedral void layer, we are getting a 2 tetrahedral voids. This will keep on repeating itself, and in the end of the calculation, you see, for all the atoms, there are n octahedral and 2n tetrahedral voids available in the hexagonal closed packing structure. In ionic solids, anions form the closed packed structure and the smaller ions, cations, occupy the void. So in that structure, whatever these octahedral and tetrahedral voids you are counting, these voids are occupied by the smaller cations. Here's another tricky point. If the cation is small, because we know tetrahedral void is smaller in size compared to octahedral void, so small cations will occupy tetrahedral voids, and if the cations are large in size, they will occupy octahedral void. These will occupy tetrahedral voids.